Hey there, stats enthusiast! Welcome back to our AP Statistics series on Unit 5 Sampling Distributions. I'm Goldie, and today we are going to be focusing on creating a sampling distribution for a sample proportion. We're going to be determining parameters for setting up our sampling distributions, as well as finding and interpreting probabilities and parameters for those sampling distributions. So without further ado, let's dive right into today's lesson. In our last video, we did a simulation activity where we went over the differences between the population distribution, the sample distribution, and the sampling distribution. And we ran a simulation to really see the differences between all of those. In today's video, we are going to formally define what a sampling distribution for a sample proportion is. And to get into that, we're first going to summarize some of the main points from that activity. So the activity was the video before this. If you did it, awesome. We're going to recap it here. If you did not do the simulation activity video, you will still be able to understand what we did and what we saw in that activity here. So we first defined a few vocab terms. When we talk about a parameter, we're talking about a number that describes some aspect of a population. N is the symbol that describes the total population size, so capital N. P, lowercase p, describes the total population proportion for us. And then mu describes the total population mean. Now we'll get into means within a few videos. Today we're going to focus on the proportion. And then a statistic is a number that is computed from sample data. So lowercase n represents the sample size that we get. P hat is the sample proportion, and X bar is the sample mean. So these are values that we obtain from our sample. And then we had a discussion about sampling variability, and we understood that sampling variability was something that naturally happened, that naturally occurred whenever we took a sample. Ideally, when we take a sample, we want our sample to represent our population. And as long as we do a good job of taking our sample, it usually does, with some natural sampling variability. And we expected that, and we know that that's going to happen, and we know natural sampling variability is going to occur. For our population distribution, what we started on first, we talked about how there's only one population distribution, and that for proportions, this is categorical data that is broken up into a success and a failure. So the graph of a population distribution is a bar graph. Success, failure, whatever your variable is broken up. You have some sort of population size. So in this instance, our population size is 400, right? We have 140 successes, 140, if I can get my pen to work, 140 successes and 260 failures. The proportion of success, P, in here, because we have 140 successes, we take 140 divided by our population size. Our proportion of success is 0.35 for our population. Okay? So this is something that's true about the population. There's only one population. And then when we go to take a sample, we take a sample of the population, right? And there's many possible distributions for a sample. It's infinitely many, okay? Each sample distribution will contain a p hat value, which represents the proportion of successes. So here's one example, right, that we take from our population. And again, in the ideal world, our sample distribution will be an exact replica of our population distribution. But normally, due to sampling variability, it's not going to be an exact replica. Pretty close though. So we still have a bar graph here, success and failure. Our sample size, because we have 18 successes and 22 failures, our sample size is 40. Proportion of success, when we look at that, we take 18 divided by 40. Our proportion of success is 0.45. Now in the population, P was 0.35, but now in our sample, we have 0.45. So that difference, again, is due to natural sampling variability. And we would expect If we took another sample, that would be different. Our proportion of successes would also be different. Now that brings us to the meat of our lesson today, and that is the sampling distribution. So the sampling distribution, there is only one sampling distribution. We made a simulated sampling distribution in our activity, but the true sampling distribution, there's only one. The sampling distribution takes all possible p-hat values from every possible sample distribution, and it has to be the same size, n, and it puts them together. Okay, so we said there's an infinite number of sample distributions that you could take in our example of n equals 40, and it puts all of those possible p-hat values together. And this creates that single unique sampling distribution, and it has some common properties among all sampling distributions. So the mean, let's talk about symbols here. The mean of a sampling distribution for a population, for a sample proportion, this should say for a sample proportion, is mu sub p hat. So in that subscript, we have p hat. Now the reason we have mu sub p hat is because, as we're going to see, our sampling distribution is going to switch over to a quantitative value. Okay, so instead of a bar graph, which our population and sample distribution both were, the sampling distribution is going to switch into a quantitative distribution. So it's the same thing. Since it's switching to a quantitative distribution, I do have a standard deviation of a sampling distribution for a sample proportion. Again, that should say sample proportion there. So it's going to be sigma, because that's our population, sub p hat. Okay, so it's very important you understand those two symbols are going to be the mean and standard deviation of a sampling distribution for a sample proportion. So if we take all possible samples of size n equals 40, and this is just n equals 40 is just our example that we're doing, and then you find those p-hat values and put them together in a distribution, this is what you're going to get. Again, this is a little simulated, but that dashed line represents the ideal sampling distribution. Okay, and what you're going to find is that your mean in this situation is 0.35 and your standard deviation is 0.0754. Okay, now our mean, that should look familiar because the mean of our sampling distribution is equal to the population proportion. Okay, so that's pretty easy to see. The standard deviation, how does that relate to all of this? How does that relate to my sample proportion or my population proportion? Well, we're going to check it out here. Okay. First, let's talk about that center of a sampling distribution. So when we start taking samples, we have to revisit a question we had a bit earlier in the semester, which is how trustworthy is a statistic at being an estimate, right? We take a sample, we find some statistics. Now, how trustworthy are those statistics? Because ideally, again, we want that sample to represent the population at large, and we want it to do it well. So a sampling procedure is biased, or it's not very good at being an estimate if it systematically overrepresents certain segments of the population. Okay. Now, when we say systematically overrepresent or underrepresent, that keyword systematically means that there's something in the way we sample that is always going to result in a biased sample. So the examples we talked about a few units earlier would be if you sent out a survey and your sample was people who responded to the survey, right? We have a potentially biased source of data because the people who are represented in our sample tend to be strong opinionated one way or the other. They tend to have maybe a little bit more free time to answer a survey, et cetera, et cetera. So they are overrepresenting certain segments of our population, which is why to avoid bias samples, to avoid that situation, we want to make sure that our sample uses random selection. Okay? And this is specifically when we are sampling. When we are running an experiment, which we tend to do more in comparative studies that we'll get into the next section of notes, we want our experiments to have random assignment. Okay, so we have to have some sort of random selection with a sampling situation, or random assignment with an experiment. And this is because we can avoid those biased samples to make sure that our sample represents our population. So the key term here I have underlined, unbiased estimator. So we say a statistic can estimate a parameter, and if it can be used to estimate a parameter, it's called an unbiased estimator. Okay? So in symbols, this is what it looks like for our sampling distribution for a sample proportion. So the center of our sampling distribution is equal to our population parameter. And that's what we just talked about, how our mean of the sampling distribution was 0.35 and our population proportion was also 0.35. Okay, so those are going to be equal as long as you randomly select. Okay, now let's get into the shape, because I know you saw the shape of that sampling distribution. No matter the shape of the population distribution, which when we're talking about categorical data, it really hasn't, we don't say it has a shape, right? Bar graphs don't have shapes. So no matter what the population distribution is, the shape of the sampling distribution will always be approximately normal as long as a condition called the large counts condition is satisfied. Now, the large counts condition is actually based on the idea of the central limit theorem, which is a big important theorem we're going to talk about very soon, I promise. But for now, in this class, we have these guidelines called the large counts condition that allows us to check to make sure that we can use a approximately normal distribution for our sampling distribution. So here it is. Here's the condition up on the screen here. It says n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. Right? So basically it checks that the number of successes, the proportion of successes in our sample, and the proportion of failures in our example both are greater than 10. Okay? And this is checking basically to make sure that our sample size is large enough. When our sample size is large enough, we can say that the distribution will be approximately normal. We can never say it'll be exactly normal. Okay? Never exactly normal. It'll always be approximately normal because, nothing's perfect, right? But it's more of a consequence of that central limit theorem that we're going to start talking about in notes 4. And I actually have an activity for you guys right before we get into that too. Okay? So that's the shape of the sampling distribution. The last thing we want to talk about is the spread, is that standard deviation. Now, we know that statistics vary from sample to sample due to natural sampling variability. But we also know that larger samples are going to have less variability than smaller samples. That was another thing we saw in that activity. Larger samples have less variability. Okay? The spread of the sampling distribution does not depend on the population size, but instead it depends on the sample size, okay? And this is a very important thing to note. No matter what your population size is, does not matter, but it does depend on your sample size. So for independent samples, basically when we sample with replacement from a population, or independent samples such as like rolling a dice, flipping a coin, when we have things that we sample that are naturally independent, or if we sample with replacement, the sampling distribution has a standard deviation of this, right? The sampling distribution of our, the standard deviation of our sampling distribution is equal to this formula, the square root of p times 1 minus p all over n, okay? That's for independent samples. Now, if you are sampling without replacement, like we did in our simulation activity, or like we usually do when we sample from a population, we don't pick a person and then put them back and pick again, right? We usually take, okay, if our population is, 400 and we take a sample of 40, we take those 40 things. We don't put them back after each time we collect them. We just take the 40 out of the 400, right? That's usually how we do it. The standard deviation of the sampling distribution will actually be slightly different. We'll have there is a slightly, different formula. However, we have a rule. And as long as this rule is followed, the difference is negligible, meaning we're going to use this formula on the screen when we sample without replacement as long as this condition is satisfied. Okay? Now, before I show you this condition and call it what it is, note that this condition is unique to AP statistics and just kind of basic statistics in general, okay? It's not the end-all be-all rule, but it's just a guideline that we follow here in class, okay? This rule is called the 10% condition. We checked it to make sure that when we sample without replacement from a finite population, it will not affect the proportion of successes so much that our standard deviation formula will be incorrect, okay? So as long as this condition is what we call satisfied, we can use that formula for the standard deviation of our sampling distribution. And here's the 10% condition, okay, written out as a formula. It says that n has to be less than or equal to 10% of our population size, okay? So basically, it's making sure that n is small enough so that when we do sample without replacement from our population, that our proportion of successes isn't going to be affected in a major way, okay? So we say sample size is less than 10% of our population size. Now, sometimes our problems are going to have a set population. You know, n is 400, n is 2,000, right? But a lot of problems that we'll see, they won't mention a population size. So like if I want to sample from all high school students in the United States, right? How many high school students are there in the United States? Well, it's probably not going to be given in the problem because we really don't know at any given time. So what we'll do instead, and what you'll see in the examples we do, is we describe n with words. And we go on to assume that it's large enough, right? If my population is all high school students in the United States and I take a sample of 100 high school students, is 100 less than 10% of my population? Yes, absolutely. That is a fair assumption. So we'll set up this formula, but in place of n, capital N, we'll put words to just describe the population and then go on to say it's satisfied and we can use that sampling distribution. Okay, now I want to remind you here, we have this condition. However, remember the spread of the sampling distribution does not depend on the population size. I know that we have the population size in this 10% condition, right? That is just checking to make sure we can use the sampling distribution standard deviation, okay? That is not saying that the sampling distribution standard deviation depends on the sample size, okay? That is a very important distinction to make. This, if you look at the formula for the standard deviation of our sampling distribution, it only depends on that population size. Or excuse me, that sample size. Look at me. Okay, so in our example above, I said that the standard deviation of our sampling distribution is 0.0754. So if we check that, if we plug in our values for P and our value for 40, N is 40, you can see that checks out. That's how we get that standard deviation. Okay, and one last thing to note here about this, you only need to check the 10% condition when you are sampling from the population. Okay? When you have an experiment, we are not sampling and the condition does not need to be checked. Okay? Again, the 10% condition is there to make sure that you can sample without replacement from a population and not affect P in a meaningful way. Okay? If you're not sampling, you don't need to check this condition. Okay? You need to make sure that your experiment groups are independent, but in a well-designed experiment, they're going to be. So it's not something you need to check. Okay, let's get into a problem. Example problems. We have two examples I want to go through here. So the first one, we're going to do basically a 4-step process to answer this question. So a recent study looked at the percentage of young adult women who get less than 7 hours of sleep a night. In this study, they say that 45% of women get less than 7 hours of sleep at night. What is the probability that a random sample of 50 women will result in a sample proportion of 50% or higher? Okay. So step one, we always want to communicate. Okay, we want to communicate the parameter and we want to write down what are we trying to find. Okay, so communicating the parameter is P. We're dealing with proportions here. And P is going to represent the proportion of women who get less than 7 hours of sleep a night. Okay, so when you communicate that parameter, you want to write it down in context first. Write it down in words what it represents. Okay, and then you want to write down what are you trying to find. Well, we want to try to find that in a random sample, we get a sample proportion. So P hat is our sample proportion of 50% or higher. So we are trying to find this probability. So that's step one. Okay. Step two, we create our sampling distribution. How do we create our sampling distribution? Well, we create it by finding shape, center, and spread. And in order to find shape, center, and spread, we have to check those three conditions we just went over. Okay. The first condition was random, right? A random sample has to be taken, and it was. Okay, it was stated in the problem, a random sample of 50 women. So if a random sample was taken, that allows us to find the center of our sampling distribution. And we can say the center of our sampling distribution is equal to 0.45, okay, which is what this study is saying 45% of women get less than 7 hours of sleep a night. So we're calling that our population parameter. So that's the center. If it's random, we can have the center of our population, the center of our sampling distribution equal to our population proportion. Independent. So we call it independent because we technically want to make sure that whether we're sampling or an experiment, we have independent samples. Because we are taking a sample and we're collecting a random sample, we have to check that 10% condition. So here's an example of what I say when we put our population into words, because our population is young adult women, and we don't know how many young adult women there are. There are a lot, right? So we set up our 10% condition, say 50 less than or equal to 10% times all young adult women. So I just put into words what our population is, and we're going to call that a safe assumption, okay, right? 50 less than 10% of all young adult women, that's pretty safe to say, right? So we know we can find the standard deviation of our sampling distribution. So we're going to use this formula. 0.45 is our P, our population parameter, and our N is 50. So we plug those values in, and we get 0.0704 for our standard deviation. And lastly, we want to check our shape. Okay? Our shape is our shape normal, because we want an approximately normal distribution. So we check our large counts condition. And checking your large counts condition, you have to substitute in your values and show this inequality, right? So n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. You don't actually have to evaluate those numbers. You can just show it like I have on screen and say, therefore, the sampling distribution will be approximately normal, okay, by checking that large counts condition. All right, so now step 3 is calculate, okay? So we communicated, we created our sampling distribution, or you can also call that step conditions, right? Step 3 is calculate the probability by converting your data into a z-score and using technology to find the probability. This is also in the problem where you would draw a curve. I will always draw the curve because I love visually communicating what I'm finding. But on the AP exam, if you're taking the AP statistics exam, drawing a curve at this step is considered optional. Okay. So what are we trying to find? Well, again, it goes back to step 1, right? We are trying to find the probability that the sample proportion is greater than or equal to 50. And we just found out that P hat follows a normal distribution, is centered at 0.45, and has that standard deviation of 0.0704. Right? We just created that sampling distribution in step 2. So now we're going to take this and convert it to a z-score. So to convert it to a z-score, remember you take that 0.5, subtract the mean, and divide by the standard deviation. Okay? And that gives us the probability that z is greater than or equal to 0.710. So on my calculator, you don't write down your calculator speak, but I wanted to show you exactly what it is. Okay, our lower boundary is 0.71, Our upper boundary is positive infinity, 0 is the mean, 1 is the standard deviation because it's a standard normal distribution. And we get this as our probability. Okay. And here is the curve sketch for you, because I like drawing it, what we're trying to find, right? Once we get that z-score of 0.71, we can draw it on our standard normal curve, and we're going to shade the area and shade the probability that we are trying to find, right? And this is what you put down on your problem, okay? Don't put down any calculator speak, but you do have to show the work for the z-score, okay? Show what's on the screen there. That should be the minimum that you show in terms of work for this solution. Okay, so that's what we just did. Our last step is conclude, right? We want to conclude the problem by answering the question in a complete sentence with the context of the problem. Okay, so we say the probability that a random sample of 50 women will result in a sample proportion of 50% or higher who get less than 7 hours of sleep at night is 0.2389, right? Kind of a mouthful, okay? There are different ways you can write it. It doesn't have to be exactly that, but you want to put the context to it, right? You want to say, hey, the probability that our random sample of women who get less than 7 hours of sleep at night, the probability that we have that sample proportion of 50% or higher, 0.2389, okay? 0.2389. And that's it, okay? Now, at this point, I always get the question, why the heck did we do that, right? Why do we care? Why do we care what the probability that we get 50% or higher if our population is 45%? Well, as I've been saying, sampling distributions are the basis for inference. So when we get into Unit 6 and Unit 7, we do this, right? What we just did, we basically do again, but then we draw inferences from this, okay? We answer questions that allow us to apply this information to the entire population, right? And when we get into those units, we'll talk more about it. Right now, we're doing the problem, we're understanding sampling distributions, and we're going to apply it a little bit more in Unit 6 and Unit 7 as well, okay? All right, we're going to have one last example here in this video where Dane is not going to study, okay? Okay, he's not going to study for a statistics final. So unfortunately, the final has 100 multiple choice questions, lucky him, and there's 5 choices for each of those questions. We're going to assume all questions are independent and that Dane has given himself over to the gods of chance and randomly guesses on each of the 100 questions. So Dane says, you know what, I didn't study, I'm not even going to look at the questions, I'm just randomly going to guess for every single question, and I'm going to do it independently of the next, okay? Good luck, Dane. So there's a couple questions we can answer here. One, what is the parameter in the context of the problem? Right. This is something we would do on a 4-step problem as well. What is the parameter? Well, in the context of the problem, P is going to represent the proportion of questions he gets correct, because we're kind of curious, right? If Dane does this, what are the chances he gets a certain number correct, right? So P is going to be what we're interested in. The following values, N and P. Well, N is going to be 100 because there's 100 multiple choice questions, okay? And P is going to be 1/5, which is 0.2, because the probability he gets that correct is 0.2. Now, you might try to argue with me, isn't 100 the population, right? Because there's a total number of 100 questions. But for us, we would say that, okay, he's going to take 100 questions, right? And in theory, there's an infinite number of questions he could take, right? We just had 100 questions on this final. It represents a sample of questions that Dane is going to have for his statistics final, okay? So that's why lowercase n, our sample is 100, and the proportion of success is 0.2. Is the sampling distribution approximately normal? Why or why not? Okay. Now, when we ask this question, you have to remember what condition means that the sampling distribution will be approximately normal. So if you think back, the shape of the sampling distribution depended on the large counts condition. Okay, so that's what you will check. Okay, put those numbers into the large counts condition, n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10. Now in this case, you can see that the large counts condition is satisfied. When you take 100 times 0.2, you get 20. 100 times 0.8 is 80. Both of those are greater than 10, and the large counts condition is satisfied. So we can say that the sampling distribution will be approximately normal. The next question, is the sampling distribution unbiased? Okay. Now, what does unbiased mean? Unbiased means that our sampling method does not over or underrepresent our population, right? So because each question is randomly guessed, we would say that the sampling distribution is unbiased. Our sampling method is unbiased, and therefore the center of our sampling distribution will be equal to our population proportion. Last question, do we have to check the 10% condition here? Okay. We said the 10% condition was so that we could sample without replacement from our population, okay? Because we are not sampling, however, we do not have to check the 10% condition, okay? Why are we not sampling? Well, he's guessing on each question, okay? And so because each guess is independent, we can calculate the spread of the sampling distribution without having to worry about that 10% condition. Okay. So what are the following values here? So because all of our conditions are satisfied, we can find the center and the spread of our sampling distribution. So the mean is going to be equal to the population proportion, and the spread, we're going to substitute those values we have in for this spread. Okay, 0.04 is going to be our spread. And it's a normal distribution. So now we can answer the question, what is the probability that Dane will get between a 25% and a 50% on the test? Okay. All right, Dane, let's see. So let's write down what we're trying to find. We're trying to find that his sample proportion is between 25% and 50%. And we already created our sampling distribution. We showed that the conditions were met, and then it's approximately normal with a center of 0.2 and a spread of 0.04. So if you remember, when you have a probability between two values that you're trying to find, you have to find the z-score for both of those values. So you're going to take 0.25, subtract the mean, divided by the standard deviation, and you're going to do the same thing for 0.5. Subtract the mean and divide by that standard deviation. And you'll get a z-score of 1.25 and a z-score of 7.5, which is very large z-score. Okay, we can draw that. All right, you can see the z-score of 1.25, and a z-score of 7.5 is actually off of the standard normal, because the standard normal really only goes up to 3 and a little bit beyond 3. What we visually show 7.5 is off the charts here. And I had the probability to be 10.56%. Okay, so on our calculator, remember what you do, lower boundary, upper boundary, 0, 1, and that's how I got that 0.1056. Okay, and then the last thing I want to do is just make sure I put that in context of the problem. The probability that Dane will get between a 25% and 50% on the test is 0.1056. Okay, so you know, Dane, you can think about if that's going to be good enough for you to not study for your statistics final, or if you're going to want to do some studying and not decide to guess.
And there we have it, folks. The sampling distribution of a sample proportion has officially been dissected and explored from all angles. Remember that these ideas we've discussed here are crucial towards building our foundation for statistical inference. So please practice and ask questions. In the next section of notes, we are going to be creating a sampling distribution for a difference of sample proportions. If you found this video helpful, don't forget to hit the like button and subscribe to my channel for more AP statistics content. Until next time, I wish you endless statistical success. I will see you in the next video.